Hello, welcome to another video on binomial expansions, and today we're looking at quite a wide variety of things because what we're effectively looking at is all the sort of things that often end up being part B's or part C's for exam questions on binomial expansions. In other words, what are the things we then use a binomial expansion for after we've found it initially? So, with that said, let's just get launched straight into some examples because that's the best way to show what it is we need to be able to do. So, for one of the purposes, and you saw from the title of this video, one of the uses of binomial expansion is to find approximations of things. So, for instance, we have in the part A of this question, find an expansion up to and including the x squared term. Okay, admittedly, to save some time in this video, I've already found the answer to that earlier. So that is the answer to the part A, but it's worth pointing out if you're unsure how to do that or want to see the working for those sort of questions, do go back and have a look at some of my other videos on binomial expansion that show how to do these sort of questions in general. Anyway, the bit we're interested in though is now the part B, because the part B says use your expansion to estimate the value of the cube root of 1.6. Key things there are they tell you that you have to use your expansion. And therefore, if you just plug in 1.6 and cube root it on your calculator, you'll get no marks because they're wanting you to use your expansion that you found in part A. So, how are we going to do that? Well, for a start off, don't be fooled. Of course, cube root is just the power of 1/3. So therefore, straight away, we start to see some parallels between what we're trying to find and what we've been given because, of course, we've already found the expansion for 1 plus 6x to the power of 1/3, and now we're trying to find 1.6 to the power of 1/3. So they have the same power. So therefore, if we want our expansion to be useful, we need the 1 plus 6x inside the brackets to be being equal to 1.6. So therefore, it is finding what we want it to find. So all we've got to do is then solve that mini equation. So if you do that, you will end up with, in this case, x equals 0.1. What that's telling you is in order to make your expansion find what 1.6 to the power of 1/3 is, you need to plug in x equals 0.1 into your expansion and it will find basically an estimate for 1.6 to the power of 1/3. It's an estimate because of the fact that we haven't completely done the entire expansion. Because we stopped after only the x squared term and didn't do all the other terms afterwards, partly because that's impossible because it's an infinite expansion technically, but because we stopped after a set number of terms, that's why it's only an estimate. It's like having a number and rounding it to a certain number of decimal places. We're, not writing the whole number, so it's only an estimate for what the full number is. So therefore, that is what we're doing here, but let's actually go ahead and do that. So, therefore, 1.6 cube rooted is approximately 1 plus 2 lots of 0.1 minus 4 lots of 0.1 all squared. And so, therefore, if you type that into your calculator, you will get, what will we get? 1.2 minus 0.04, so that's 1.16. There you go. So that's approximately what the cube root of 1.6 is, apparently. However, something to bear in mind is to remind yourself that expansions are only valid for certain values of x. So that's something we looked at in a previous video, what values of x a expansion is valid for. And therefore, for this particular expansion, we have 6x instead of x inside the brackets, so therefore we replace it in that notation. So if that's telling us that x, or the modulus of x, is less than 1/6, or in other words, x is between 1/6 and minus 1/6. That's important because it means we're only allowed to plug in x values that are in that interval into our binomial expansion and it come out with a number that makes any sort of logical sense whatsoever. Luckily, that made sense for our question here because x equals 0.1 is in that interval, because 1/6 is roughly 0.1666, etc., etc. So therefore, that's why we were allowed to plug x equals 0.1, and that's why it will find a estimation that's vaguely correct. Whereas we do have to watch out when we move on to some other questions. So in this other question, we've got a new expansion, 1 minus 6/25 x to the power of a half now, again up to and including the x squared term. Again, to save time, I've already found that for us, but the interesting part is the part B, because it says, by considering the value of the expansion at x equals 25/4. That's interesting straight away because they've actually told us the value they want us to use, but I'll talk more about that in a bit. But we want to find the estimate of root 3 to 3 decimal places. Now again, good news, we've got the square root of 3 there, and we've got the expansion with a power of a half as well. So they're both to do with the power of a half. But therefore, you might be tempted, if you hadn't read that they want you to plug in x equals 25/24, you might be tempted to try and find the x value yourself and go ahead and do that. So if you were to do that, you would realize the only way 3 to the power of a half is the same as 1 minus 6/25 x to the power of a half is if 1 minus 6/25 x is equal to 3. We make the thing inside the brackets for the binary expansion equal the thing we're trying to estimate inside the power. So if we do that, we then could get minus 6/25 x equals 2, and then, therefore, x is equal to 50 over minus 6. In other words, minus 50 over 6. The problem is, this would be a bad idea to do. There might have been a bit of foreboding about that by the fact I did this working in a pink square. But, therefore, why is this a problem? Well, as I said before, you do have to watch out these expansions are only valid for certain x values. And if you look at the expansion's valid values, in this case, it would be the values between 25/6 and minus 25/6 if you were to work it out. And the problem is, minus 50/6 is definitely not in that interval. So therefore, even though plugging x equals minus 50/6 into 1 minus 6/25 lots of x would make it 3, which therefore in theory would be finding the square root of 3, in reality, doing this with our expansion wouldn't find the square root of 3 because the expansion doesn't work for that x value we're plugging in. So therefore, that's a bad idea. We can't do that. And that's partly why they've suggested a different value. This one, you'll notice, is in the interval. I say notice, I mean, it's fractions, so you might not be able to tell. 25/24 is only a little bit over 1, and then 25/26, ultimately 24/6 is exactly 4, whereas 25/6 is just a little bit over 4. So 25/24 is definitely in that interval. But there's something else we then have to watch out for, therefore. Let's find out what happens if we actually do plug in 25/24 into our expansion. Well, first of all, let's plug the x equals 25/24 into the original brackets. So let's plug it in at this stage. And if you were to work that out, we'll end up with 1 minus 1/4 to the power of a half, which is, interestingly, 3/4 to the power of a half. And you'll notice that that isn't the square root of 3. We're finding the square root of 3/4, which is not directly what they want us to find. But this is important because we can do something to the square root of 3/4 to get the square root of 3 quite easily. If you apply index laws to this, or write it in surd form, however you want to say that, 3/4 square rooted is square root of 3 over square root of 4, and square root of 4 is 2. So interestingly, if we plug 25/24 into our brackets, what we're finding is not the square root of 3, we're finding the square root of 3 divided by 2. So therefore, all we've got to do is plug in x equals 25/24 into our expansion from part A. So therefore, we would have 1 minus 3/25, lots of 25/24, minus 9/1250, lots of 25/24 squared, and that will come to 0.867187 blah 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 blah. Obviously, I'm just stopping writing it there, but you keep the whole number as a decimal on your calculator. But we're aware that isn't our estimate for root 3 yet. That's root 3/2. So therefore, root 3 is approximately double that. So therefore, what we've got to do is double our estimate that we just found just then. And that will get you 1.7343 blah, 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 blah. So the final answer is 1.734 to 3 decimal places, obviously paying attention to how much accuracy the question wanted. Interestingly, if you were to actually find what root 3 is on the calculator, to 3 decimal places is 1.732. So actually our estimate was fairly accurate. Obviously, it's wrong on the 3rd decimal place, but we ultimately only did the first 3 terms of the binary expansion. In reality, if you included more terms in the binary expansion, it would provide a very good estimate, probably, for root 3. But there you go. On to another type of question they can sometimes ask as an extra part, or even actually just straight away as one big question. So they want us to find the coefficient of just the x squared term for this entire expansion here. Now the thing to bear in mind is, once again, part of this question would just be finding the binary expansion for that little bit that requires the binary expansion, which we already said earlier was that. So I am going to use that answer as part of this. But therefore, a lot of students might then be tempted to sit there and literally sit there multiplying fully the brackets of 2 minus 11x plus x squared times by 1 plus 2x minus 4x squared. But we don't need to. And I'll explain why in a second, but the other aspect is, why was I able to stop at the x squared term in my expansion? Well, the reality is, if we only want the overall x squared term, as we're doing this expansion times by some more stuff, we're definitely not going to want the x cubed term or so on and so forth, because they're going to be even bigger than once they've multiplied by some other things in the other brackets as well. However, I have included the first term and the second term, the constant term and the power of 1 x term, because, again, we've got to be aware that the x squared term in the 1 plus 6x to the power of third is not the only way I'll get an x squared term overall. This is where we now have to be tactical. As I said, you could fully multiply the brackets, but it's a waste of time. All we've got to do is consider, if we're taking things in this bracket and multiply it by things in this bracket, what things multiplied by what other things will lead to an x squared term overall. So, therefore, if we were doing that, the only things that would lead to an x squared term overall is if I did the x squared times by the 1 in the other bracket, which should get me x squared. If I did the minus 11x times by the positive 2x in the other bracket, which should get me minus 22x squared. And then if I did the 2 times by the minus 4x squared in the other bracket, which is minus 8x squared. Those are the only parts that we actually care about multiplying by each other, because those are the only parts that will lead to an x squared term overall. So it's about being tactical. Although you could fully multiply out the brackets, it's a waste of time. You're not going to be given the marks to give you time to do that. So be sensible and realize what are the actual important parts that are going to lead to the specific bit of information you want. So in this case, we're going to end up with minus 29 x squared, so therefore the coefficient as the final answer, as they only ask for the coefficient, make sure we understand, or we show we understand what a coefficient means. It's just a number in front of the algebra. So the final answer is minus 29. Cool. And then the final type of question we're looking at today is binomial expansions with an unknown power. So, how do you do this? Ultimately, whenever they do this in exam questions, where they just start putting a bit of algebra in place of where you're normally used to seeing a number, they're testing your confidence with the method that you're meant to be doing the question. Are you confident enough to do the exact same method that you're normally used to doing, but doing it with algebra instead? And then sometimes, as is the case with this question, you're going to end up having to set up an equation based on that algebra to then find what that missing value is. But the reality is that these questions aren't really any more difficult than a normal question, just as long as you're comfortable doing algebra. So, another little point to note is we actually don't know what sort of value we have. We don't know if n is a positive integer value, or whether it's one of the fractional or negative powers that we've been dealing with more recently for binary expansion. The reality is actually that doesn't change the method. although normally for binomial expansion with positive integer powers, we'd be using a completely different method to the fractional and negative powers, ironically, the formula we use for fractional and negative powers does still work for positive integer powers as well. We just don't normally use that formula because it's a bit more fiddly to use if you do know that it's a positive integer power. There's a much nicer method that we looked at before for doing those sort of scenarios. So, therefore, as we don't know whether it's a positive integer power or a fractional power, we have to do the fractional power method because that's the method that always works rather than the other method which only works when it's a positive integer. Anyway, let's get on with actually doing the question now. Now, it's worth mentioning they are only talking about the x squared term in the question. So therefore, although you could find the entire expansion, again, it's a good idea to be efficient. So therefore, I'm only going to find the x squared term in the expansion. So I'm going to go straight to that part of the formula, which is in the form booklet. So apparently, according to the form booklet, it's that. However, of course, you're aware that that's the expansion for 1 plus x inside the formula booklet. So therefore, instead of x squared, we're going to do 7 over 4 x and then all squared like that. N would normally have been replaced with a number by now as well, but of course that's the point of this question. We don't know what n is. So therefore, proceeding on with this, we end up with n times by n minus 1 divided by 2, and then 7 over 4 all squared is 49 over 16, lots of x squared. Now, the interesting part of this is it means that the coefficient that we got for the x squared term is n, lots of n minus 1, all divided by 2, lots of 49 over 16. Whereas the question is saying that the coefficient of the x squared term should have been 1715 divided by 128. So therefore, we can set up this equation that I've done here and then solve it to then find what n possibly could be. So let's go ahead and do that. I could start by dividing both sides by 49 over 16. And if we were to do that, you would end up with 35 over 8. We could then times both sides by 2, which will end up with 35 over 4 on the right-hand side. And then you'll spot that this is just a quadratic. So we've then just got to solve this quadratic to get the possible values of n. Now this is the point at which you're looking at that thinking, ugh, that doesn't look very nice. So therefore I should now basically use the quadratic formula to help me with this, because you don't want to be solving this manually. So it's 1 plus or minus the square root of 1 squared minus 4 times 1 times 30 minus 35 over 4, so it'll end up being a plus 4ac instead of a negative 4ac technically. And then all divided by 2a, so that's 2. There you go, and work that out. If we plug that into a calculator, we get n is equal to minus 5 over 2 or positive 7 over 2. So there you go, those are the possible values of n, done, and we have finished the question. Amazing. Okay, and that is all I wanted to cover in today's video. It's worth mentioning I've given you a little bit of a tour across the things that they can ask you sometimes in exam questions, but by no means is that a guarantee of the only things they could ask you in exam questions. It's, of course, as always, about being adaptable. But there you go. Hopefully you found this video useful, and I'll see you in a future video. Goodbye.